half of all the stars in the sky are binaries. And so when you look at the spectra, you will see them go around each other. And so you, in principle, can measure the red shifts and the blue shifts as they go around each other. You see Doppler effect. If they come to you, you see blue shift. If they go away from you, you see red shift. So in principle, you can determine for each one of those stars the velocity in orbit, the radius of their orbit, and of course the period of the binary system. So it's an extremely powerful tool in astronomy if you have a binary system when the stars exactly do this to determine all these quantities that you would like to know. I first would like to show you now some slides. The first slide, oh, I have to lower the screen, by the way, that would help, wouldn't it? The first slide is a spectrum made in the laboratory of hydrogen, helium, and calcium, and sodium. It shows you emission lines, no absorption lines. These lines are produced by lamps, and the frequencies are very well known. Here you see the famous sodium yellow lines. So here's the red part of the spectrum, and there's the blue part of the spectrum. So we know these frequencies, we know these wavelengths very well. And here you see the spectrum of the sun with all these absorption lines that I mentioned to you, plastered with absorption lines, and each of them can be identified. These are due to calcium, iron, hydrogen, and so on. Here is the blue part of the spectrum, here's the green part, and here is the red part of the spectrum. And here you see the basic idea behind a binary system. Suppose you have a binary system that only one star is visible and the other one is invisible. And the one star shows you 3 clear absorption lines. Then as the star moves around the center of mass, you see that all these lines drift in unison. And out of this information, you get the radius, the velocity, and the period, assuming that you are on Earth in the plane of the orbit of the stars. If you have a binary system whereby both stars are visible, so you get the spectrum of both stars, then you'll see the Doppler shift of both stars in the spectrum. Here we have a simple case that we only have 2 absorption lines, not to confuse the issue. And so in the case of one star, the shift will be towards the left of the 2 lines, but the other star, the shift will be to the right. Because if you have a binary system, when one star comes to you, the other star goes away from you, and vice versa. So now you are very lucky. Now you have an ideal situation that you can find for both stars the radius of the orbit, the velocity in orbit, and the period for each star, which of course is the same for both. And here you see real data. You see here, first of all, the emission lines which are measured in the laboratory that I just showed you. They're always done simultaneously with the measurements. You always must be sure that you have a good calibration of your wavelength. And this spectrum A, the top spectrum, is of a star, a binary system that has a period of 20.5 days. And you see here single lines, if you have good eyes. That means at this very moment, both stars move relative to you at angles of 90 degrees, so you don't see any Doppler shift. But now look here, later in time, you see that this line has split in 2 lines, and this one has also split in 2 lines. Clearly, one component is coming to you, and the other component is moving away from you, and so you get all this useful information in astronomy by making the